So it's almost the end of the day. And thank you for joining us. And Tom and I, we're going to tell you a little bit about solutions that in storage that are geared towards AI infrastructure that provides economic solutions that are sustainable for the future. So today, my name is Mohammed Al-Batal. I'm a Chief Technologist within the Office of CTO at Seagate. And Tom Prohofsky, he's one of our technologists also in the Office of CTO. We're happy to tell you a little bit more and leave some time for questions at the end. So, you know, as a storage provider, we've been monitoring and you know, through IDC and others and looking at the amount of cumulative storage that we're going to see by 2028. You know, 400 zettabytes or close to 400 zettabytes, and the latest data is even going to half a yottabyte of data being created. We're not going to store even close to 10% of that in the world, and it'll be lucky if we get close to that. Sustainability of our resources, power, and material, et cetera, that will become a very important thing to manage, and including, you know, all the budgets in the world will not be sufficient to provide solutions that at the solution level to manage all that data. So some of it will go away, and some of it will be stored, but we have to provide more innovation for sustainability and reduction in complexity and foundational technology that will bring us to a more efficient model at the end of the day. So some of the efficiencies that we've worked on within the hard drive industry, which is 90% of the world repository of data, will continue to grow at a scale that beyond what we've done in the past, right? With HAMR technology, heat-assisted magnetic recording, that level of growth between generations of drives and releases of drives will be increasing at a different rate, at a different slope, as well as the sensitivity to environmental solutions that are around it, right? Like, you know, the rest of the compute is going for, you know, cold plate cooling. Is it possible in the future that we'll see more SSDs going to cold plate and more HDDs going to cold plate to reduce vibration and acoustics and you know, transition within the next future 10 years, transitioning away from acoustics and air movement to cool is inevitable. So we're looking at what that means for areal density growth, what that means to, you know, creating an environment that would allow us to do this. And the most important part of this presentation is going to be how is software going to also benefit from an efficient way of creating interfaces on the devices that we have that is cohesive and streamlined, so it can feed, direct connect feed the GPUs and the CPUs and the infrastructure. So 3 areas of innovation that are geared towards efficiency. Let's not forget that, you know, the idea is data is essential for the compute to be meaningful, right? And we're going to need to try to preserve as much as we can of that fuel that will help us get the most out of our AI infrastructure. And, you know, that simplification, cartoonish view of the mass capacity reliance in that infrastructure with regards to unstructured data and structured data All types of storage and memory in the pyramid will be needed. There's no specific one that is going to replace or substitute another. It's all cohesively working together to create the best TCO possible. It is inevitable that some types of storage will get hotter, will be able to perform better, and some will actually perform less but get more capacity. It's a fine-tuning equation that is dynamically adapting to the specific usage model of specific AI models as they're reinvented to suit the usage model. So in the training, though, in the training aspect of an AI and the feedback loop that takes from the inferences, as the data cools down, it ends up being in the pool, in the large pool in the pyramid, and then fed back after cleaning and prepping. It gets fed back into that loop. So I think some of you have seen something similar to that displayed and explained in detail. We're not going to spend all the time on that, but just as identification of where the pyramid starts and where it ends. Really, you can flip it around and think about it as that the unstructured data that's inputted into the models is where mass storage will be predominantly, and then fed back from the output from the GPU that's coming at a rate, as well as some input feedback of the inferences back into the GPU will skip that pool and eventually rest back in it. So what did we do with regards to the growth rate of the HDD? So we're looking at 50 terabyte this year in terms of the capability to prove that technology. So the proof of 5 terabyte platters and 6 terabyte platters will happen this year. Now, when do we release it is a little bit later in time. There's always a gap between testing a platter, testing the media, testing the heads, testing the capability, and then releasing it. And in that case, we're in the about to release 40 terabyte. It takes a little bit longer to get to the 50 terabyte devices and release them. But that's kind of if you look at the way the slope was going, it was much slower growth in the capacity. Now we're almost doubling in about 4 years of time. The infrastructure of the drive has not changed much in terms of mechanics. They still have rotational media. They still have some aluminum. Some, in our case, it's glass media for Seagate. But the head technology has evolved significantly, and the usage of picosecond pulse lasers within that solution has really substituted the need to provide very high energy magnetics on the head, which any high energy magnetics tend to be more and more difficult when the media coercivity is getting tighter and tighter. So the grains are getting tighter. You need to increase the magnetic field and the energy to magnetize it. Instead, Seagate has been working for the last 20 years on HAMR and heat assisted. And the idea is that you can apply a picosecond pulse of laser to heat that material, the few atoms that you're actually trying to write at a given time as the disk is rotating, and provide that pulse with enough heat that now less energy is needed to magnetize that surface. Thus, basically, overall, it's an more efficient model of writing onto data, and it allows you to write on even denser material and a longer life of retention of that data. So it's even enabling that that media to retain that data almost indefinitely. So as I said, you know, the current testing is currently between 5 to 6.5 terabyte platters, and by the time we're releasing 50 terabyte drives in 2028, we'll be testing 10 terabyte disk. So that kind of scale or slope of growth and capacity is enabled with HAMR, and the whole industry is geared towards moving in that direction. It's just, you know, we happen to get there first, but it takes, you know, the whole industry is moving or announced that it will move in that direction as well. Now, with that in mind, you know, having larger capacity is our number one goal, right? As a company who is supporting that, the bottom of that active data pyramid, right? Data that is being used actively. We have to provide more efficient storage. So by releasing a 40 terabyte drive versus existing 24 terabyte drives, you're providing 40% more power efficiency. You know, you're providing space efficiency at that same rate. So it really enables us to keep up with the data growth that we showed initially and continue to store close to 10% of that data in the future. With that in mind, we're exposing, you know, the time frame around the beginning of the next decade it will be 100 terabyte devices out there in 2032. So that means we have to do something with the interface. We have to start thinking about how can we increase the interface to maintain the same reliability of the data and capability. We're doing other things with regards to CDL, command duration limit. We're doing other things with regards to regen or logical depup so that the drive can self-heal without having to rebuild the drive because of a single head failure. So that is a critical. There was a session that Curtis and Dave from Seagate did earlier on both of these subjects. There were, you know, I invite you to watch the video for that, but it is essential that in a drive there are 20 heads. There are typically 20 heads, 10 platters, and if one of them failed today, if you're not using regen, it's going to go back to warranty or get crushed or whatever. The idea is that it's okay to lose some performance during the time of healing rather than rebuild the whole drive and get the whole fabric, the back-end fabric busy, right? So we're really going in the direction of where we are in flash today, where, you know, flash, you have a very small OP, but you're capable of rebuilding pages or even devices in some cases. The idea here is very similar, and the goal, the end goal, today we're not there, but the end goal is to have self-healing drives so that you create better reliability equations as you grow the capacity to 100 terabyte. It's necessary. The other thing that we need to do is pay attention to the interface and the viability of the current interfaces in the future. You know, do we want to streamline or stay? And we'll talk more about it. Another thing that happens when you go to those densities in tracks per inch is that, you know, you're exceeding 1 million track per inch. That's, you know, on a thin piece of paper, you got about 3,000 to 4,000 tracks on the edge of that paper. So it really is getting to the point where it's not really feasible to allow for vibration to exist. You can try with a lot of vibration dampening material. We're trying by reducing the airflow as much as we can, creating better flow through systems. But as we approach those densities, it has to be a quieter environment. So systems, teams, I don't know how many of you design systems, but I think a lot of it is, in our world, going away from high screaming fans and noisy fans to more cold plate cooling. In the next decade, will need to be considered, at least, to create a quieter environment for hard drives. That means, we have to do some simulations to start with. We showed that we can actually get denser. So instead of today's predominantly, anywhere from 60 to 100 some drives, you can exceed the 100 drive per 4U in a 19-inch rack if you stack them a little closer and use cold plates on one side of the drive. We've shown different models of, I don't have the whole set of the models that we've done in this presentation, but we've shown that there's an OpEx benefit from not having spinning fans and using power on fans. And there's, if you have a shared infrastructure in the data center with a cold plate capable, open loop, water-cooled, water-chilling solution for compute, if we can leverage part of that, and remember, we're still less than 10 watt per drive, so even 100 drives, that's in a 4U, 1.2 kilowatt is not that much to cool in comparison to, the beast, GPUs that are burning, almost a megawatt per rack. So we're asking for a little bit of cooling in an ash rate 27 environment in the data center. Eventually, it will benefit us quite a bit in terms of creating a quiet environment for the hard drives. So some of these simulations showed that there are some benefits that vary. Anyway, I would like to shift here to the software discussion. Just wanted to give you an overview of what we're doing on the hardware side, and Tom will take over from here. Thanks.
Thanks, Mohammed. I hope you got a taste to realize that this isn't your dad's hard drive. This is a very sophisticated material science wonder that you can still buy with a single paycheck. Or multiple of them for a single paycheck. So, whole box. So I want to switch gears literally to the software. And first I want to start off with how we're going to manage cost is our opinion is the only way it's going to be done is by dynamic provisioning and using the right layer for the right job. And if we look at these two machines, they've been purpose-built and refined for their job at hand. And just because the sports car can go really fast doesn't mean pickup trucks are dead. They still have a role to fill. And people who have tried to combine them into El Caminos and things that are like neither good at either of those, being fast or hauling, those usually don't last very long, although they make great novelties and lowriders. But the point is, use the right tool for the right job. And so when we looked at the complement of SSDs and HDDs, Seagate creates and makes both of these. We see them working together, but one of the big things that came when NVMe hit the market was that it pulled away in a different interface, and the inertia of the major players buying hard drives were kind of satisfied staying on SATA and living with that interface, its strengths and weaknesses. And so we've seen the ability to really come and unify these and been in leadership, and Mohammed's done a lot of work at making sure the standards can embrace a hard drive as a peer with SSDs. So not for us. We're not doing this because it makes our job easier. In some ways, it makes our job harder. We're doing it, hopefully, for everybody in this room so that the consumption of drives could maybe in one day be a single interface, and we're done with having to deal with multiple standards. So what we've done is looked at the details of what did SATA bring, and then what does NVMe bring. And we're gotten to the point where it's now truly compelling, and why there's CPU power efficiencies and other things on this list. I think the real hero of the story is this RDMA capability. So when we can RDMA directly from an NVMe drive, hard drive or SSD, out through a SmartNIC with RDMA acceleration onto the network, now we can compose with any tier from any machine, and that liberates and creates an agile, future-proof way to provision exactly what you need and no more in the future. So when we looked at this and where we are today, we have for SAS, if you remember SAS, we still sell them and there's still people consuming them, but there's inertia there. They required a SAS controller and a SAS expander, and you got all the benefits of SCSI and 20 years of an interface that's been beat up and refined and does exactly what it does really well. But there's added hardware complexity and failure modes there. SATA, with the CPUs having some native SATA interfaces, it was able to grab a chipset and start connecting up drives, a small number, but still connecting up direct attach. But now that's going away. If you've noticed, some of the chipsets are starting to defeature that SATA interface, and it's not going to be around forever because of other demands on the processor. So when we brought an NVMe hard drive to life, we decided to show it off at NVIDIA GTC earlier this year. It's the same, pretty much the same bill of material. So it's not like this is going to make your hard drive $50 cheaper. It's the same pieces, but a different protocol. We speak a new language, and we're able to connect up directly to a Bluefield 3 DPU and get that benefit of having it just work and be able to present a hybrid storage array. And then our vision for the future is just continue that on and have the lanes come right off of the DPU of choice. We're fans of DPU. They seem to be, once again, a purpose-built, refined engine to do exactly what you need, getting storage bytes onto the network to feed the beast. So we took this demo and we did this DPU demo where we put a few SSDs and a bunch of HDDs and allowed the DPU to be doing the hot to cold and cold to warm and transitions and really hide all that movement that happens with all your data sets. I mean, everybody talks about training, but not all your models are training on all the data all the time. There's not enough GPUs for the exabytes of data out there. So as your data sits for a while, this system just automatically will help age and put that on the right tier. The other benefit, because we're staying with all block device and all the hardware acceleration of a block interface, we get that RDMA not only benefiting the DPU side, but it also benefits the direct memory placement into the GPU. So that full hardware automation path now goes for HDD and SSD. At scale, this is still a cartoon. This isn't even near scratching the surface of scale. But if we have a whole bunch of those DPU-enabled arrays that are a hybrid with SSDs for burst buffer and checkpointing, and HDDs for all the data sets over all the revisions and all the raw data and all the metrics, now we can go through the full life cycle with a solution that is scalable and can do everything from training to data prep. The DPU brings another benefit because it's at the intersection of storage and networking. It can participate in some of the sophisticated networking congestion management because the spines of these of this high-speed networking aren't over-provisioned. There can be congestion between the top-of-rack switches. So being able to use that DPU to help make the whole solution work is very helpful. One final note here is, as we think about security, the DPU also helps create its own little trusted environment that's outside of the client's security. So if a client gets rooted and compromised, the DPU is another barrier and reduced attack surface, especially over a general purpose CPU doing the same storage array. So as we look at NVMe over Fabric especially, it's really interestingly poised at this position between volatile and non-volatile, or between memory and storage, and it lets that NVMe interface of hard drive and SSD go up and directly into GPU and HBM. So I want to take this picture to talk a little bit about what can be done today with Linux in some ways that Seagate's enabled that some people might not know about. Inside Linux, there's the logical volume manager, and the logical volume manager has two modes. One, traditional operating system. I own all the hard drives, I manage the hard drives, I make sure all the threads in my CPU don't stomp on each other by some locking mechanism, typically spin lock in memory, but it has no concept of neighbor. LVM2 has a special mode called shared volume groups, which uses an external locking service. And when you turn that on, now you can have clients, multiple clients, directly attached or believe they have direct attached storage through NVMe over Fabric. And they all see those drives as their own, but when they talk to LVM2 to create volumes, extend volumes, mount volumes, they go through that external locking mechanism. So we improved the two locking mechanisms that were there, SandLock and DLM. If you get on your laptop and Google the man page for LVM Lock D, you'll see those two methods. We did a third called the in-drive mutex. And what that does is ask the collection of drives or the collection of DPU arrays in this picture, can we lock that particular, that unique UUID for that volume or that volume group? And so by doing that, we allow all these nodes to work together. So where in the original solo mode, the LVM2 was just keeping the cores in one service working, now it allows all the cores and all the nodes to consume all the storage. The one way to use this cost effectively is to create a volume per data set and then mount that volume with your favorite file system. I'll just put XFS up there for a placeholder right now. On the node that's going to be doing the processing. But then somebody here is going to say, like Wendell will say, wait, Tom, I'm training. I want multiple GPUs to be reading my data. And that's when we flip over into read-only mode, because your data set, your training data set isn't changing. So you can do that volume read-only, and we can do it in multiple nodes that get a shared lock. That shared lock is making sure no one node accidentally writes the data, so that you can know that during your training phase, all nodes can see all the data and it's consistent. So we have a way to now have what I've seen in other presentations called a lockless data path. The application, the GPU, the DPU, the CPU or GPU can go directly to the drive over the fabric, get its data without any distributed file system being involved, without any other layer. It doesn't have to check with anybody because the metadata has already told the system how to prepare the volume and the access to it. So then the decision is where and how to do caching. I can put a cache using a tier 0 cache and pull in the local drives to be part of the shared volume group and get the benefit of LV cache there locally, or not, and with more of a lower cost solution. So you have optionality in how you deploy, and then the cache could also be used if needed to get performance in the tiering of the DPU enabled storage. So let's keep moving. So then with that LVM2, we need an orchestration to help get the quality of service, to get the resiliency, to set up the volume groups with the right striping or rating or whatever you need for your quality of service. And there's a project called Atapo LVM, which is a CSI driver for Kubernetes, that is aware of volume groups. So you can tell Tapo, I have this volume group medical data. So let's say we're in a hospital, and it will know which Kubernetes nodes have direct access to that volume group, either through JBOF and PCIe or through NVMe over Fabric. And then during the scheduling of the job, Kubernetes will affinitize or put that pod where there's the fastest direct path to the data. So this is a realization of the vision of don't move the data to the GPU, move the GPU or CPU to the data and get the benefit of moving less data across the wire in the network. All right. That was doing locking in the drive where we can, or near to the drive, to create a clustered environment. On the other end is solutions that lock in the clients and create a distributed cache or metadata. And so this is done through some proprietary file systems that we've heard in this room or the last couple of days. And then there's an open source project too that I'm aware of that can do these features. And this is for larger scale, for hybrid cloud, where you're trying to do not only SSD and HDD, but you're also doing those in different availability zones. And you want to optimize what resources you have where, and your disaster recovery plan for how many copies where, and get the throughput to feed the GPUs. So your first decision is, am I going to use the tier 0 and get the benefit of the SSDs that are right there next to the GPUs and get the low latency benefit but have a limited throughput and IOPS, or do I want to set up a cache externally and place my SSDs across a high-speed network where I can burst in and get dozens and dozens of SSDs working on the problem in a bursty fashion? The next is the metadata cache. So the metadata cache needs to be distributed and resilient and scalable. And this does exist in open source projects, along with metadata nodes that can actually be caching inode data. So this is where you get a better than just LV block level cache. The actual file ID and inode and offset can be the key for the cache, so the clients get a faster response than traversing a file system to actually find the block. And these these solutions are both memory and SSD backed, so you can right size your performance and scale your deployment. The next tier down is really your blocking and tackling of your data. This is where you're deciding how much SSD nodes I need and how much HDD warm data and not hot data do I need, more throughput or bulk or maybe your rich media. And the key aspect here to look for solutions is the migration between those, because the only way it's going to be cost effective is if Seagate doesn't ask Mohammed and Tom to move the data moves the data and figures out when it's cool and when I don't need it. It needs to be behind the covers, under the covers, behind the curtain, and in such a way that it's declarative. We can set up a policy either based on access time or naming conventions or whatever, so that the number of data nodes that are SSD and the number of data nodes that are HDD can be optionally used to fulfill the service level agreements that are needed. And then finally, under all of this is the active archive of the blob nodes that are able to take everything and anything you throw and keep it there until you're confident you don't need it. A lot of AI is growing and maturing. It's like our kids. I mean, how many times do you train your kid to clean, empty the dishwasher? You have to do it more than once. At least that was my experience. I didn't get them doing it right away. It took lots of training cycles. AI models are the same thing. We get better at training. We as parents get better at parenting. We learn how to better do our job. Data scientists get better at modeling. They get better at feature extraction. They get better at the algorithms, so that raw data that you might have thrown away in the past is best held on to until you've really gone through the life cycle of that model development. All right, so this gets into our conclusions on what to consider from what you just heard is, first, how will model development be tracked and measured? This is not what you're hearing a lot in SNIA, the 3 days here of SDC, but the planning process of what am I doing and how am I going to measure it is crucial. And so once you understand what my model is and how the data that's feeding it is going to be tracked, then I can measure it and I can store it and I can make sure that the quality of service that I need is getting provisioned, but no more. I don't need my model to always sit in memory forever. That's a waste of memory. The other thing to consider is how will data sets be managed over the life cycle of the project? And this gets into that how to tell the computer, the subsystem, the storage system, how to move things on my behalf so that I'm not the one moving to a more cost-effective tier. And so deciding ahead of time your naming conventions, any flags for saying this data is cool, this data is done, is to the best of my knowledge, those kind of things so that they can be put into the rules engine for the data migration. And then how will archives be handled, and will be both remote and local be used so that you can avoid data extraction fees. So if you are in a hybrid cloud, you may choose to do some processing in the cloud, but don't try to extract it, do some feature extraction locally to help reduce those hidden costs. I touched a little bit about it with the LVM2 solution, but if I can decide if my data prep needs to be read-write many or read-write once, I can save some money. A read-write many distributed file system comes with burden of CPU cycles and baggage, because when you do a unified namespace of all the files everywhere, now the HR files are in the way of the manufacturing files, which are in the way of the engineering files that you're trying to go through. And so when you can separate these things out and manage the data sets on a little finer granularity, you can decide, do I need to be doing data prep in parallel, or is it a pipeline and I can have a single read-write once to be hydrating those data sets and the prep files that they generate. It's a way to save money and make a more cost-effective use of your subsystem. Finally, that question about availability zones. Spanning availability zones is great for disaster recovery, but not everything needs that. If you can regen some of the data or have backups, you might decide that you don't need to span availability zones, and that can help control networking costs. So it's not necessarily a storage cost, but it's a hidden storage cost because your network bill is going up as you increase your WAN capability. And then finally, the duration. It really data and keeping data is a question of how long. How long do I need this? How long should I keep the raw data around? How long, or should I start subsampling the raw data and getting rid of like data sets? These kind of decisions, if you do them up front, you can set the policies, capture that knowledge, and move on. Keeping track of model revisions. There's benefit of, taking the picture of your kids by the door and seeing each year how tall they got. There's benefit of measuring your models over time and seeing which ones worked well or which ones didn't work as well over time, and have the data scientists be able to look back at the historical performance. So keeping that data it helps the agility of the team, which at the end of the day is really our limited resource. And then how much do you really need for scratch space? What does that look like? Finally, if you can't see it, you can't improve it. So telemetry and gathering the data is crucial. So when we did the distributed LVM2 solution, and we could use Prometheus and Grafana to gather all the metrics for every volume and its use on every drive up to every node, we could have full visibility of bottlenecks and throughput and latency and all. And that allowed us to tune and see if there's problems or set thresholds to notify us if there are. You got to be able to measure it and gather that data to be able to refine your process. So in the end, it all comes down to efficiently using everything that you have. Use all the arrows in the quiver. There's no one best place to do AI. You do AI through this whole stack. And dynamically provisioning is the key, that letting the orchestration or the scripts or the scheduling that you do have the knowledge on how to use these different classes of storage and get the whole life cycle intent into that model. Secondly is, automate that caching and tiering and migration. That was why we did that demo at GTC. Is we want automatics. We like it when it just works. So keep doing those kind of things and building them into the system where you can, so that they're doing the migration and cost savings for you. And then the upfront planning. So being able to look at what the model is doing and refine it for the use cases, that you have is key to being efficient with your resources. It's easy to spend a lot of money. It's easy to over-provision and just go bigger, better. But at some point, our CFOs come back to us and tell us that your budget is flat or going down. Now figure it out. Maybe you have better CFOs. I don't know, but we hear that. Okay, we're gonna stop here, and I'll take some questions. But thanks for listening.
Thank you very much.
Any questions from the crowd? Wendell.
Promise to do a question.
Thank you.
You talked about some of the issues with drives being RDI, with the high areal density, and you do some regen to recover the drive. How do you see the MTBF hammer drive compared to MR and things like that?
Things like what?
Bit rot.
Yeah, so in reality, the current plan, so yeah, go ahead, repeat it.
The question was, with the higher density that we're pushing with HAMR, how do we see MTBF and failure rates, and we could add retention and other concepts with HAMR?
Yeah, so the bottom line is that we won't release a drive from Seagate unless it's equivalent or better in terms of its ability to, from a retention perspective, from a reliability perspective, AFR, and all these things are currently either at or better from where we were with PMR. Now, the question is not about the retention or the availability. It's about the RVI is a problem that we lived a long time ago and moved on from. Acoustics, on the other hand, come in at different frequencies, different environments that are becoming more damaging to existing infrastructure. And we do the best we can to moderate the fan speed in normal temperature conditions. It's when temperature goes up and you have a fan failure condition, that's when really the fans start screaming and causing RVI or causing acoustics to damage and create some errors and due to noise and unable to stay on track. In the future, with the increase of number of tracks per inch, that tolerance is mitigated with today's systems. And in the future, you're going to continue to add more tri-stage actuator capability where you're able to track at an even higher refinement, but that adds cost. So at some point, what we did is we can live up to 1 million track per inch with tri-stage actuators. Beyond that, we're asking for help from the industry at the data center level, is basically more efficient to add more intelligence in the drive, or is it better to just start utilizing the ecosystem, use cold plate? You tell us, we'll do it. We can control it. We will continue to provide the same standards. But can we design a more efficient solution if we leverage what's available in terms of liquid cooling? Those are the questions.
And I want to add on to Wendell's question just directly. HAMR has been running for, 5 years ago, we could have maybe released a HAMR drive, and you wouldn't have liked how some of its end-of-life characteristics. And we had to chase down every one of those failure modes until it could run as long or longer than our PMR drives. And the amazing analysis that was done to get us there is documentary worthy. It's really an engineering feat that I haven't seen too many times in my career, and it is stable and it is reliable and it.
As we stated, as I was saying before, it's more designed for energy efficiency as well. So you would think the laser is just on for a picosecond, for a few picoseconds, yeah. Right? So it's a pulse, but it's creating efficiency in terms of how much magnetic field you're going to have to apply. Yeah. Versus, you either have to augment it and wear out your heads, or you heat up and then you gently use your head. So it's really a combination of capabilities that were added to enable better reliability in the future.
How about a drive spin down? That's been talked about for a while.
That's still being applied today. So if you heard Meta in some of the sessions, they talked about a whole layer of spin down drives that they're using today.
Question in the back, yeah.
Firstly, I'm very appreciative of the agency in general because you have been bringing innovation to SDC technology for years. Like, it's so amazing to see a technology that was invented decades ago and still being so competitive and safe. My question is, in the data center and enterprise industry, the power loss prevention is a critical factor. How critical it is for your use case and how do you implement it in an SDC trial? Is it similar to what you use or?
Because of the fact, so let's repeat the question. So what about power loss protection? Do we have supercaps? Do we have batteries? No, we actually use the inertia of the rotational media in the drive to actually recuperate, just like an electric car, we recuperate some of that energy to flush our cache. Because we have that rotational media, spinning down in the process, we basically leverage that. So that's currently implemented.
Yeah, so when you turn on write cache enable, it is going to our cache that is an SRAM based media, but the back EMF of that drive and those platters have enough momentum and to hold the charge up enough so that we can move it into a NAND or NOR to save it. And so that's just the way we roll, and it's been
one benefit of rotational media is
Right.
that you get some energy back out of it.
Good question, thank you. Yes?
What's the biggest challenge to getting to the 50
Biggest challenge?
Biggest challenge.
Well, the question is, what's the biggest challenge to get to 50 terabyte drive? The key is there's no big thing. This is an army of ants that we fight. It's getting a little bit of margin everywhere. Where our margin was here, we bring it down to here, and then where our tolerances and margins here, we tighten it to there to get that extra little bit. And it's just, the secret is there's no secret. It's relentless engineering, doing your analysis and figuring out every spot where there's wasted effort and squeezing it out. The key was when we did HAMR, it's put us on a new S curve.
That's the point. HAMR was the biggest challenge. Trying to get HAMR made it easier made it more possible for us to make those bigger leaps, right? And media innovation. So there's the material science team, there's the head team, creating our own lasers. Seagate is going to be one of the largest producers of lasers because we have 20 in every drive, and we got 40 million, 50 million drives a year. Go ahead.
Quick question. When you're track following with HAMR, does your laser remain stationary or can you move the laser? Because in your picture, it looked like the head was about 3 tracks wide.
Now, the laser is part of the head, and basically, as the rotation, it's still the actuator. It's moving with the actuator, so the laser will move along with the writer.
But what I was wondering is, as you're track following, can you focus the laser on different spots and essentially?
Now you've gone beyond my knowledge of that. So
The precision, there's many precision points in there, and for all practical purposes, like Mohammed said, you can think of it as just part of the writer head in its fix. And so where the reader is finding the track, the writer is right there with it mechanically. So but it's not on during reading. You only turn the laser on when you need to soften the ferrite material to flip it with a lower write energy.
But to hit 1,000,000 TPI, you have to have, the head has to track follow.
Yep, it has a tri-stage actuator, so you're following it 3 different layers of actuation, right?
Yeah, so you're following, like, I'm assuming you're doing some sort of quadrature burst servo, down on the surface so that the head hits center. But if you had a laser that could maybe not move, but you could, direct its beam to little pieces of that, you could increase your track density without having to increase your servo action.
We'll take that to the servo team. I really like your idea.
The challenge isn't getting down to that one
We're
grain or
timing
the
it.
other. It's trying to reduce the energy for the noisy neighbor for the extra track. So a minute change isn't going to help us.
There's a transducer too below it, and it's pretty
I
complex.
think we're out of time.
Out of time. Thank
So,
you very much.
Thank you. Appreciate you hanging
All
out.
right.